Hello, in this video we will deal with the Nobel Prize in Physics from 1913 awarded to Heike Kamerlingh Onnes for his investigations on the properties of matter at low temperatures which led inter alia to the production of liquid helium. We're going to look at some information coming from the official Nobel Prize site about his work, some biographical information summarized, and a summary of the award ceremony speech. And in the next video, we'll deal with the Nobel Prize lecture given by Kamerlingh Onnes himself. First, some work information. When different substances are cooled to very low temperatures, their properties change. In 1908, Heike Kamerlingh Onnes used an ingenious apparatus to cool helium to liquid form. Fluid helium was carefully studied and also became an important aid for the cooling of different substances and charting their properties at low temperatures. In 1911, Kamerlingh Onnes discovered that the electrical resistance of mercury completely disappeared at temperatures a few degrees above absolute zero. The phenomenon became known as superconductivity. As you can see, this is directly quoted from the official Nobel Prize site, and you can see the link to it here. And here you see a picture coming from Wikipedia. High temperature superconductor. And as said, the phenomenon of superconductivity was discovered by Kamerlingh Onnes. There's some biographical information also coming from the official Nobel site, summarized by me. In his doctor's thesis, theoretical as well experimental proof was given that Foucault's well-known pendulum effect should be considered as a special case of a large group of phenomena which in a much simpler fashion can be used to prove the rotational movement of the Earth. In 1898, he, this is of course Kamerlingh Onnes, published a paper, General Theory of Liquids, which dealt with the kinetic theory of the liquid state, approaching van der Waals law of corresponding states from a mechanistic point of view. This work can be considered as the beginning of his lifelong investigation into the properties of matter at low temperatures. In his inaugural address, The Importance of Quantitative Research in Physics, he writes at his well-known motto, Door meten tot weten, that's Dutch, and translated into English it means knowledge through measurement. Appreciation of the value of measurements which concerned him throughout his scientific career. After his appointment to the physics chair at Leiden, Kamerlingh Onnes reorganized the physical laboratory known now as the Kamerlingh Onnes Laboratory in a way to suit his own program. His research was mainly based on the theories of his two great compatriots, J. van der Waals and H.A. Lorentz. In particular, he had in mind the establishment of a cryogenic laboratory which would enable him to verify van der Waals' law of corresponding states over a large range of temperatures. His efforts to reach extremely low temperatures culminated in the liquefaction of helium in 1908, bringing the temperature of helium down to 0.9 degrees Kelvin. He reached the nearest approach to absolute zero then achieved, thus justifying the saying that the coldest spot on Earth was situated at Leiden. It was on account of these low temperature studies that he was awarded the Nobel Prize. Later, his pupils, W.H. Kasom and W.H.G. de Haas, Lorentz' son-in-law, conducted experiments in the same laboratory, which led them still closer to absolute zero. Other investigations in his laboratory, which gradually gained in importance and international fame, included thermodynamics, the radioactivity law, and observation on optical, magnetic, and electrical phenomena, such as the story of fluorescence and phosphorescence, the magnetic radiation of polarization plane, absorption spectra of crystal in the magnetic field, also the Hall effect, the Dirac constant, and especially the resistance of metals. A momentous discovery in 1911 was that of the superconductivity of pure metals, mercury, tin, and lead at very low temperatures, and following from this the observation of persisting currents. The results of Kamerlingh Onnes' investigation were published. Many foreign scientists came to work in his laboratory. The laboratory gained fame throughout the world through the training school for instrument makers and glass blowers housed in it, founded by Kamerlingh Onnes in 1901. This is a summary of the biographical information. If you want to read the complete biographical information on the Nobel Prize site, follow this link. And here you see a timeline of superconducting materials and also the temperature at which they start being superconductive. You can see in 1900 it was very close to absolute zero, and now in 220 there are already superconductive materials at 250 K, which is slightly under 0 degrees Celsius, about 23 degrees. Here you see a periodic table of superconductive elements with an experimental critical temperature. Here you can see, well, you can read yourself. If you want to study this more closely, you can pause the video. This is also coming, by the way, from Wikipedia, as is this picture. Then we go to the award ceremony speech by former counselor T.H. Nordstrom, summarized by me again. As early as 100 years ago, research into the behavior of gases at various pressures and temperatures gave a great impetus to physics. Since this time, the study of the connection between the pressure, the volume, and the temperature of gases has played a very important part in physics, and particularly in thermodynamics, one of the most important disciplines of modern physics. In the years 1873 and 1880, van der Waals presented this famous law governing gases, which, owing to their great importance for thermodynamics, were awarded by the Royal Academy of Science in 1910 with the Nobel Prize for Physics. The thermodynamic laws of van der Waals were laid down on a theoretical basis under the assumption that certain properties could be attributed to molecules and molecular forces. In the case of gases, the properties of which are changed by pressure and temperature, or in one way or another do not agree with van der Waals hypothesis, deviations from this law occur. A systematic experimental study of these deviations and the changes they undergo due to temperature and the molecular structure of the gas must therefore contribute greatly to our knowledge of the properties of the molecules and of the phenomena associated with them. It was for this research that Kamerlingh Onnes set up his famous laboratory in the beginning of the 1880s, and in it he designed and improved, with unusual success, the physical apparatus needed for his experiment. It is impossible to report briefly here on the many important results of this work. They embrace the thermodynamic properties at low temperatures of a series of monoatomic and diatomic gases and their mixtures, and have contributed to the development of modern thermodynamics and to an elucidation of those associated phenomena which are so difficult to explain. They have also made very important contributions to our knowledge of the structure of matter and of phenomena related to it. Whilst important on its own account, this research has gained greater significance because it has led to the attainment of the lowest temperatures so far reached. These lie in the vicinity of the so-called absolute zero, the lowest temperature in thermodynamics. The attainment of low temperature in general was not possible until we learned to condense the so-called permanent gases, which since Faraday's pioneering field in the middle of 1820 has been one of the most important tasks in thermodynamics. Olszewski, Linde and Hampson had prepared liquid oxygen and air in a variety of ways, and after the war, having overcome great experimental difficulties, had succeeded in condensing hydrogen at temperatures down to minus 259 degrees Celsius. All temperatures down to 14 degrees from absolute zero could be attained. At these low temperatures, all known gases can easily be condensed except for helium, which was discovered in the atmosphere in the year 1895. By condensing this, it would be possible to reach still lower temperatures. After both Olszewski and de Watt, Travers and Jacquarot had tried in vain to prepare liquid helium, using a variety of methods, it was generally assumed that it was impossible. The question was solved in 1908, however, by Kamerlingh Onnes, who then prepared liquid helium for the first time. I should have to cover too much ground if we were to report here on the experimental equipment with which Kamerlingh Onnes was at least last successful in liquefying helium, and on the enormous experimental difficulties which he had to overcome. I would only mention here that the liquefaction of helium represented the continuation of the long series of investigations into the property of gases and liquids at low temperatures, which Kamerlingh Onnes has carried out in such a praiseworthy manner. These investigations finally led to the determination of the so-called isotherms of helium, and the knowledge gained here was the first step toward liquefaction of helium. Kamerlingh Onnes has constructed cold bath with liquid helium, which permits research to be done into the properties of substances at temperatures which lie between 4.3 degrees and 1.15 degrees from absolute zero. The estimate of these low temperatures is of the greatest importance to physics research, for at these temperatures both the properties of the substance and also the course followed by physical phenomena are generally quite different from those at our normal and higher temperatures, and a knowledge of these changes is of fundamental importance in answering many of the questions of modern physics. Let me mention one of these particularly here. Various principles borrowed from gas thermodynamics have been transferred to the so-called theory of electrons, which is the guiding principle in physics in explaining all electrical, magnetical, optical, and many heat phenomena. The laws which have been arrived at in this way also seem to be confirmed by measurement at our normal and higher temperatures. That the situation is at very low temperature not the same, however, has amongst other things been known to Kamerlingh Onnes experiments on resistance to electrical conduction at helium temperatures, and by determination which Nance and his students have carried out in relation to specific heat at liquid temperatures. It has become more and more clear that a change in the whole theory of electrons is necessary. Theoretical work in this direction has been begun by a number of research workers, particularly by Planck and Einstein. In the meantime, new supports had to be created for these investigations. These could only be obtained by a continued experimental study of the properties of substances at low temperatures, particularly at helium temperatures, which are the most suitable for throwing light upon phenomena in the world of electrons. As said, this is a summary. If you want to read the complete ceremony speech, you can follow this link, which leads to the official Nobel Prize site. You see the laureate Kamerlingh Onnes with Ehrenfest, Lorentz and Bohr. This is in Leiden, by the way. And here you see liquid helium in the superfluid phase phenomenon, but that's also observed by Kamerlingh Onnes at very low temperature. It is related, of course, to superconductivity. That's it for today. Next time we will also deal with this prize, Kamerlingh Onnes, and then we will go into his Nobel Prize lecture. For now, thank you for watching, and maybe until another time.